Okay, let's start. So we're happy to have Sasha Razborov speaking to us today. Sasha's been faculty at TTIC and also at the University of Chicago for a while now, and has been, I think, overall very, his presences have been very well felt, and is, I see now today he's back talking about math. But he has others, of course, contributions to complexity theory and circuit complexity and natural proofs. Sasha has actually become a machine learning person recently, so I don't know if you're talking about it today, maybe not. But
I can say something about it.
You see something, you can ask him about it later, ask him about his nearest papers, and I'm sure he'll tell you about it there.
Thank you very much, Nadia, for the introduction, and sorry about my voice, something happened 2 days ago, I don't know what, and yeah. Just in case you are worried, I took the COVID test yesterday, it's negative. Alright, so, as Nadia said, can you hear me? Good. And you also can understand what I'm saying, right? Not only here.
So far.
For now.
These are different concepts.
Do you understand it in the slide?
So, slightly paraphrasing what Nadia said, I've been speaking at this seminar for so many years that I don't even remember how many years, and I always tried to make some connection to things people in this establishment are mostly doing, which is machine learning and theory of algorithms. But you know, first of all, I don't know how well it worked. It's not up to me to decide. And second, eventually you get tired. So this year I will just not attempt to make any connections. I will just talk about things that I do in my spare time and very often. However, speaking of connections, there is only one thing that my long professional life has taught me. You really don't know when, how, and why they happen. Right? You cannot say what will happen out of the things you are doing. So if you ever see anything similar to what we will be doing, and it will be pure math, then just talk to me and we'll try to make sense out of it, because things are connected very often and very unexpectedly. And second, this talk is very selfish. So it's not a survey. As you see, we have lots of topics to cover. I really cannot even attempt to give a survey. Again, if you are interested, then talk to me. It is all somehow focused on my own research that I've been doing in combinatorics. All these are projects, some of them are latent, some of them are very active, and in those cases, when they are active, I will not mention my collaborators. One of them is in this room, because I will mention them, well, it will lead to something, but one thing that sort of unites all these things is that if any of you gets interested, I will be happy to talk about it. All right. So now, let's start. Any questions? Okay, good. So the first area, which is very interesting and very important, I think, is extremal combinatorics, and I put here the word asymptotic, and soon I will explain what I mean by this. So let me start with the main definition. The main definition is very simple. We have a couple of graphs, H and G, and their role is very different. H is a fixed template, triangle or something. G is considered to be huge. And we look at homomorphisms from one graph to another. And let me remind you that a graph homomorphism is just a mapping that preserves edges. That preserves edges, in particular, if two vertices are connected with an edge, they should be mapped to different vertices, also connected by not you look surprised.
So you see me create new edges.
May not create new edges in case. No, yes, make new edges, which means that if two vertices are not connected within edge, then they can go to a couple of vertices connected with an edge.
Oh, so new because it adds edges to H, but not
Yes,
to G.
and that's it.
Yeah.
That's graph homomorphisms. So, and now we are denoted by this quantity the number, but as is customary and very natural in this area, we are interested in densities. So we always try to be between 0 and 1, and in this setting, in the denominator, you see the overall number. Oh, sorry. The overall number of mappings from H to G. So each is the density of homomorphisms, and I will have also lots of digressions in my talk. And so it's the first one that's very often it is more natural to talk not about graph homomorphisms, but about submodels, which are just right. As is written here, formally these two things are equivalent. In some contexts, it is better to deal with homomorphisms. In other contexts, it's more natural to deal with densities as defined here. Discrete.
Just as a sanity check, so the denominator here is the number of all possible mappings from H to G, and so it says what fraction of those mappings.
Yes, density, fraction, probability, choose any word you like. We want to be between 0 and 1. Thank you. More questions? Yes, okay.
So I could think of, for instance, like how many 4 cycles are there
Yes,
in G? So and it's okay if they have edges going inside.
yes, not necessarily induced.
Right.
So I will have one digression about it later, but for the purposes of this talk, it's just more convenient to.
So such as instant, the only difference here is the permutation, whether you're
It's one of them.
what's the other difference?
The first one is that it is unlabeled, right? So it's a subset.
permutation.
It's a subset. The second is that we don't allow to create new edges, and that's it here.
Oh, so here,
It's a really induced subgraph. You look at induced subgraphs
Okay,
and
okay.
you see.
okay. No, I understand over the
But
isomorphic as opposed to
yes,
homomorphic.
but all these differences are there is linear transformation that takes one to another. So theoretically, it is not important. Practically, it depends on the context. More questions. Good. And so what we are interested here, we are interested, it's the most basic program in extremal graph theory. You have a bunch of templates, fixed family, or it's convenient to assume that they are connected, and we just look at the joint densities in all possible finite graphs, and it is called asymptotic decayers. We take the closure of this set. So I will explain a bit in a second why it is better to take the closure. And turns out that this problem is extremely difficult. So it is null. Well, I would prefer to avoid here exact statements because you can always find some crazy examples.
Wait, what's the question? You said it's known? The question is to characterize.
Describe this thing.
What?
Describe this thing. Tell us what it looks like, and in particular for the case of triangles. So, and I was very surprised. Turns out that guys in statistical physics are very much interested in this case. I don't know why. They try to explain to me, but yeah. We just went through describe this set, basically say what happens. But even if you have two graphs, then it becomes extremely difficult. It is known only in a handful of cases. And again, one more digression. I also I spoke about it here many times, that it is more natural to describe these things in terms of graph limits, graphons. It becomes very natural. You don't need any closure, but right, for us it is good enough. Questions? Good. So now, in a sense, all three subtopics here I want to talk about, they are connected to two online problems, and essentially it is the case when one of the graphs in my profile is simply K2, which is just an H, and H is some other graph. Then it is not very difficult to see that du is actually connected. So du in general looks like that. We have a lower and upper bounds on the possible density of H given the H density, and it in general looks like this. So Turing-like problems, they they're defined as trying to locate this point, right, where the density of H becomes positive. So if the density of H is beyond that point, is beyond that point, then you have a constant fraction of H also. Yes.
So maybe you said it, but for K2, you're just counting number of edges, or are you doing something
Density of edges. Density. Don't use the word counting in my talk, please. So density, fraction, probability, whatever you like, not counting.
But it's just edges.
Edges, yes. K2 is just edges. The most natural question to ask, I give you what is the density of edges, what is the density of H2, and so there is a transition. So it is the standard definition. You can also define it now if you like numbers. Your n goes to infinity. You look at the graph with maximal possible number of h's, which is h3, and take the limit. Yes, Ari.
So think of this as, so you're just kind of, what profiles are possible? Like, is it possible to have this, this few edges, few low density, and this many 4 cycles, or maybe the other way around? You can have a whole lot of edges, but not a lot of these. That sort of question.
So this is the most basic question in extremal combinatorics that actually started the area, and it was a very interesting story. Yes.
Is it clear that they really need to be H-free? I mean, because they could have just very low. Okay.
I know what you are going to ask. I'm trying to sweep it under the rug, but probably not in this room. There are so-called induced or just removable lemmas here. So which means that if you have a very small fraction of H, you can remove them.
Right.
It's removable lemmas, or in the language of graphons, it's immediate.
So the green line also it's not like the red. I mean, the green line does not necessarily have to go all the way to the top. Also.
No, it has. If your graph is complete,
No, but the top doesn't mean that it's complete.
it means
Why?
the density of H's is 1.
What?
The density of H's is 1.
That doesn't mean that it's complete.
Well,
If I have n minus squared and n squared minus n edges.
Yeah, that's the probability that you will hit them is small. It goes to infinity. It goes to 0. It's all asymptotic here. That's what I'm saying.
Yeah, but is it clear that I'll necessarily have h's, like a lot of h's?
Yeah. My homomorphism will not, or key is fixed, the size of H is fixed. If you remove as many H's as you see, I will never see them. So again, all these things are better defined, and so that's what I do in all my papers in terms of graphons. I just don't want to be simpler here. So, but you are totally right, the equivalence here is not trivial, but you either do removable lemmas or you do graphons. But it is true. More questions. All right. So this problem is completely solved. It is the famous Erdos-Stone theorem. This number is completely described in terms of the grammatic number of H. And it's coming back to what Avram asked.
Can you remind us?
Yes, sir.
Can you remind us what the chromatic number is? Can you remind us what the chromatic
It is the minimum number of colors you need to color your graph so that every so adjacent vertices are colored differently. Think about a graph as a map. You want to color a map so that nodes or countries, adjacent countries share a border. Good. More questions? And so coming to what I already said, if you go to the induced setting, then it immediately becomes nightmare. So we know this thing only for very small number of cases, and relatively recently, I think maybe 10 or 15 years ago, it was a big development. People were able to do C5. And the extremal construction is crazy. It's iterated construction. So if you slightly change the thing that then it all becomes very difficult in the sort. The theorem is a gem in extremal graph theory that is never repeated. In no other context, it is repeated. Right. So I call integration primarily for the reason that I never worked on this program, but now all three subtopics in our asymptotic extremal combinatorics, they somehow stem from this theorem. The first one is a natural generalization for hypergraphs. So let me remind you that a hypergraph, graph is just a bunch of unordered R tuples. An ordinary graph is R equal to. So you can generalize all this stuff, and then it also becomes a nightmare. So until maybe 10 or 15 years ago, 15 I guess years ago, we did not know pi of h for when R is greater than 2 for any graph. Now there are graphs where we know it, but in this paper by Turan that started the area, and I cannot help mentioning that it was written in the Russian prisoner camp. So he was taken to the camp, and the chief of the camp was an amateur mathematician, and he knew who Turan was, and he worked on mathematics, and in particular wrote this paper during World War II. So he asked this question to determine simply we look at the Greek, which means that it has all possible hyper H's, and it is that open, wide open. We don't know this value for a single pair KR. When K and R go larger than R, it becomes even worse. We don't even have good hypothesis. And I spent quite a bit of time, on and off, of course. It's not what I was working always in my life, but on and off I spent lots of time on this tetrahedron program, which is the smallest open case. So, and I think I'm sort of retired from this project, but if anyone is interested, then let's talk. Let's talk about it. But I don't regret that I was doing all this stuff. Right, it hasn't been latent since 2011. Simply, I don't have anything new to say, which would be worth publishing. And I don't regret about this because this area, like most of math, is more about methods than concrete programs. So in particular, the paper was one of the first papers where the method of log algebras was demonstrated how to use it, and now it's a standard tool in extremal combinatorics. So it's more about methods than about concrete programs. All right, any questions? Good. So the second subtopic is another famous problem, which is Sidorenko conjecture. So if my graph H is bipartite, then as you can see, it means that its chromatic number is 2. I can color it in 2 colors, and pi of H becomes 0. which means that now my picture is different. So it goes, or it starts, green line starts with 0. What is the blue line? The blue line is this. If I take a random Erdős-Rényi graph, standard random model, then I am going to see roughly as many, the fraction of h's I'm going to see in a random mapping, the density of the probability that I have that my random mapping is actually a homomorphism should be roughly like that, because for every h I have an independent condition that it is mapped to an h, and there are as many h's. So this blue line, which corresponds to Erdős-Rényi graph, is always within my density profiles. So it's somewhere between green and red line, and Sasha Sitarenko made, well, absolutely beautiful conjecture that it is actually the right answer, that green and blue are the same. So, or in plain English, as I try to write it down here, so if I know my H density rho, and I'm trying to come up with a graph that has a small number of copies of H as possible, homomorphic copies, then the best thing I can do is to do it at random. It's a beautiful conjecture, and it might be less hopeless, but still it's very difficult. There was lots of work that people did on it. And so here are some results. So it really employed a variety of methods, which is always very good in math. Very different methods, but we know quite a few graphs for which it is known, and I believe it is still the smallest unknown graph. You take K55, complete bipartite graph of 10 vertices, and remove a cycle, C10 from it, which is the simplest case where it is not known. It is known for all graphs in particular, which have at most 9 vertices, and so there are powerful constructions that allow you to build Sitarenko graphs from lone Sitarenko graphs. And again, it is beautifully connected to many other areas. So, and it is something which we did with my former student and now our postdoc at Mass. Leo Carigliano, it was a small paper, but at least we did it. So, and Balazs had done it with very different methods before. So it might be not a big result, but still, yeah, it is sufficient when you prove Sitarenko's conjecture. It is sufficient to assume that your graph is biregular on both sides. So in general, it is bipartite graph. That's how a bipartite graph looks like. And you require that the degrees on each side are the same inside the side. They can be different on both sides, but you require that they're the same. Anyway, it's just something that I will be happy to return to and try to do something, particularly if there is anyone interested. Questions? Right, good. Then the third project in the first part is this. Let me remind you what Sitarenko conjecture says. So as you can see here, we have an inequality like this. When you don't add densities, you only power them to a certain power. So it's all multiplicative. And let me make one more digression. So it's another extremely difficult open problem in combinatorics. So assume that my graph is bipartite. Then if you want it in plain terms, then pi of h is equal to 0, it means that the maximum number of h's, if I give you a number of vertices n, the maximum number of h's that you can create you can add without creating a copy of h is little o of n, but little o of n is not already said, maybe it's not the final answer. So it is again not very difficult to prove that depending on the bipartite graph H, it will have this order of magnitude somewhere between n and n squared, and we know this value only for a handful of graphs. C4, C6, C10, C8 is open. But you look puzzled.
We're just playing.
Sasha,
Yes, sorry.
just to come into it. So I guess for non-bipartite graphs, like a triangle, then this doesn't hold because you can have really dense bipartite graphs that don't have any triangles.
Yes.
This is kind of saying that, well, you can't do that for bipartite.
Yes, yes. And we know we have Erdős-Corrado theorem that says where exactly it happens. If it happens in zero, then zeros are different. All zeros are born differently. So, and we normalize by n squared, but still there are various orders of magnitude. So in this case, it's wide open. And also, since it's generated some inverse, let me also mention that here it is one of the rare cases when randomized constructions don't bring the optimal result. It does not happen very often in combinatorics. Usually you apply the probabilistic method and you get your construction. Not here. So even for the case C4, you need to take the projective plane. Right? If you just do it at random, then you will get worse exponent. Yes, Manor?
Just to clarify the statement of the digression, do you mean little o of n squared there instead of little o of n? Slightly confused.
Yes, sir. Thank you. Yes. Right. So let's move to the third topic, which is more active as far as I am concerned. So both these examples, they suggest that it is natural to look at the thing. First of all, I take the logarithm of the graph profile. Logarithm means that I apply log point-wise to every density, and I look at the convex hull of this thing. And so exponentiation back, it is probably easier to describe in dual terms. Namely, so it's dual to the polytope that is generated by all those C1, C2, Ck, for which I have this identity, this inequality. Questions? In our recent work, we again studied the case k equal to 2. Even k equal to 2 creates sufficiently many problems. And so here you can make a progress, and in these two papers there were many results. So I will just give you sometimes how they look like. The abstract result is, for example, that if you want to prove that C of H1, H2 is equal to some number, then you have to give graphs where this number is realized. You cannot do it with finitely many graphs. So as C approaches to there is no single graph G that realizes this inequality, and it raises lots of questions. Here I'm a bit sloppy because I even define graphons, but can you realize every constant C of H1, H2 by a graphon? Is it rational? Is it algebraic? We really don't know anything about it. Can you even algorithmically compute it given the table it's H1, H2? Basically, almost all abstract questions here are open. And as long as concrete questions are concerned, then basically, if you look at cycles or paths, then, well, first Stoner and then us, we were able to compute it in almost all cases except for this one. Not you concerned.
Wait, I'm a bit confused.
Yes?
What's being computed here?
Sorry, C of PKPL.
What?
C of PKPL.
Of
Yes.
C of the
Two
between
paths.
between two paths.
Yes,
Okay.
between two paths, between two circles, between a path in the circle. But in this case, we were not able to do. And that's an obvious open problem. Finish it. And another open problem, which is also concrete. Sidorenko's conjecture, it basically asks, assume that you know the homomorphic density of very simple graph, like just H density, and you want to prove the green line, what is the smallest number of H's, smallest number of copies of H you can get it there, and it says this conjecture. So it's interesting to also consider anti-Sidorenko property. You fix a density of a simple graph also, like H density. What is the largest number you can get? Turns out that even that is not trivial. You can compute it. You can compute this quantity for K2. It basically corresponds to the right line. You can compute it, but again, even if you look at the next case, simply the graph of length 2, the path of length 2, then we were not able to do it. It's also an interesting open question. All right, questions? So we move on to the next. Yes, sir.
I mean, I'm curious. I mean, you kind of related to something. So for many of these, for random graphs, this is presumably much easier, at least. And you mentioned before some conjectures about the relationship between random graphs and these quantities. Are there more general, like?
No, the relation I mentioned was
very specific,
lower bound.
Right.
So if you want to go to the upper bound, so the red lines, you can do much better than random if you want to maximize the number of copies of each.
Do we have procedures that we think get close to that? Or?
Yeah. You basically take the click on the corresponding number of edges, which makes sense. So I take the click on the set of vertices, which is roughly square root of density of the graph. Then, since it is packed, then you will get as many triangles as possible, for example. The upper end is easier. But if it is an arbitrary graph, then it's already not very trivial, but relatively easy. If I change it even to this rate, then we don't know the answer. More questions about the previous part? Alright, so a couple of topics in RMC theory. It is the classical RMC theorem, and I prefer to do it in the infinitary setting. There is a simple compactification argument that will that is equivalent to the ordinary version, but I will do it later if I have time. So, and it says basically if I have K and L and I color integer numbers in any finite number of colors, C, then there always exists a set A of size L, which is monochromatic in the sense that all H's, KH's within that set L, within that set I, they are colored in the same color. That's the standard version, and it is the example that goes into all recreational books in mathematics I'm aware of. So in the simplest case, when you have two colors, red and green, and k is also equal to 2, and you are looking for triangles, then if you know only 5 integers, 1, 2, 3, 5, then you can do this coloring, and you will not have any triangles here. If you add a 6th member to the party, then you will always have a triangle no matter how you color it. So, and somehow informally, RMC theory says that every structure, in this case a coloring, always has a tiny symbol that is ordered, and it is all structured, in this case is monochromatic. That's the general principle. And it is usually things work well, which means that you can prove either RMC theorem or show that it cannot be proven, and this is one notable exception, and it is an active research project, Euclidean RMC theory. So what we have again, it is convenient to look at this space R to infinity. I don't play here with Hilbert spaces infinite-dimensional, it is simply the union of R to Dn, so all sequences with finite support. And a configuration is just a metric space A, which is embeddable, which is Euclidean, can be embedded into R infinity, so you can easily describe it in intrinsic terms. It's matrix should be of negative type, whatever. So, and we call it RMC, or just the same. Just the same as before. If any coloring of R infinity to finitely many colors has an isometric copy of it. Not you concerned.
That's
Okay, good. Yeah. So it goes along the general pattern. You color my R infinity into finitely many colors. Do I have there a copy of A or monochromatic copy? Isometric monochromatic copy of A. And turns out that now it becomes open what configurations are.
Sorry, maybe
yes,
what's the distance here that you
What?
What's the distance?
Metric space.
No, in R infinity.
R infinity? Euclidean. Euclidean distance, thank you. Euclidean. Again, I put here R infinity only for convenience,
I mean, it's finite.
but it's better to formulate it this way, more natural. And turns out that not all configurations are RMC. And the big goal, which has been open for more than 50 years, is to be able to tell what sets A are RMC and what are not.
I mean, I understand the definition, but where does this? I'm curious. Is there a natural way of thinking of this problem? I mean, where is this?
Yeah, it's RMC kind problem. So the natural way to think is just there are many problems of the RMC type. This is one of them, and it is wide open. As I said, I'm not giving any motivations, any applications here. It's purely math talk, totally useless. And we take pride in it. Yes.
Is there any connection between this Ramsey problem and the Ramsey problem on the graphs? Like, can we
Graphs,
realize?
you mean the classical RMC theory?
Yeah.
Yes, you are digging deeper than I was going to say. Many bounds, maybe all bounds, they go by, or at least essentially use a reduction from the classical RMC problem. It becomes obvious when you come to proofs. In general, this area, it misses a good notion of reduction. And yeah. More questions? Alright, good. So as I said, the project is active. I don't have any results to show. Let me just tell you a bit what is known and what is not known. And first of all, there is a powerful theorem that if I take, well, the first is obvious. The second is very obvious, it's powerful that if I take the direct product in the Euclidean sense of the RMC sets, then it becomes RMC again. And very powerful result saying that if I have a transitive group and it is solvable, transitive group acting on my A and it is solvable, then you get RMC. Concrete examples of RMC sets are here. So if I have A and all points are linear affine independent, so which means that it's a simplex, then it will be RMC. If I take a regular and bone, it will be RMC. If I take a trapezoid, then it will be RMC. There are a few more results. And negative results are, to the best of my understanding, there is only one negative result, namely that if your set A cannot be put on a sphere, then it is not Ramsey. So all Ramsey sets must be spherical. Yes?
Can you remind me the definition of a product of the two metric spaces?
Or it's it is better I formulated it this way. I think I formulated it this way, but it is more natural to think about concrete embeddings into Rm and Rm. Right? So you simply take the product within this embedding and it will not depend on the embedding. If you wish it intrinsically, then you take the matrix that corresponds to distances, square distances, and then you solve them. Good. More questions? All right. So while I'm talking, I am pressing the button, and moreover, I am pressing the wrong one. So as far as I know, it is not, it is the only negative result, and there are plenty of open problems in this area. Here, just a few. First of all, it would be very nice to show that you can do it with, you can remove, in great result, you can remove the restriction that the group of isometries is solvable. I'm not sure that it has anything to do there, but it's not known yet. And it is basically the benchmark or testbed or whatever you call it that has been in the area for 40 years or something like that. So I take the circle, I put 4 points there that are not a trapezoid. Is it RMC or not? Also wide open. All right, any questions here? All right, so Matthew, how much time do I have?
You have 10 minutes.
10 minutes. Then what I would prefer to do, I prefer to skip the next topic because it's a bit technical and move to my last topic. So extremal set theory, it is Erdős-Korada theorem, and it is one of the most, let me remind you, it is one of the most important results in the area. So it concerns intersecting families of subsets, I fix a universe, and as always, and I look at family of its subsets, and I want it to be intersecting, which means that every set in this family should have non-empty intersection. And the question is, how many such sets can you have? Then this question is actually simple. So the answer is 2n minus 1. If you want to prove lower bound, then you simply fix an element x and take all subsets that contain it. It will be obviously intersecting, and in the other direction, if I take a set and its complement, then at most one of them can be in my family. So which means that 2n minus 1 is the right answer. But let me also mention that these extremal configurations, they are equivalent to some concept in the complexity of Boolean functions. And these principal families are by far not the only ones. And so there are many configurations, and their set is is quite rich. You cannot even enumerate. So, anyway. Erdős-Koranda theorem starts with the following question. What will happen? And ends. What will happen if now I look at the uniform family, that is basically K hypergraph families in which all sets have the same size K, then clearly this question is not interesting when K is strictly greater than n over 2, because then every two subsets of size K will intersect. It's not interesting. And if K is at most n over 2, then we still have the same example. The principal family, it will have as many sets. It will be intersecting, and the Erdős-Koranda theorem basically says that that's it. So as long as K is at most n over 2, then, and you want intersecting families of K subsets, then principal families is the best you can do. And so there are many attempts to generalize it, not attempts, also results. And my last topic that I want to spend the remaining time on is one conjecture that I believe is very fascinating. It was made more than 20 years ago, and it is fascinating because when you look at it for the first time, then your first gut reaction is that it should be either obvious or wrong. And neither is the case. Anyway, so we fix a graph G, and now I look at the same Erdős-Koranda problem, only I restrict myself to the case of families, independent families, families of independent sets. Namely, I look at independent sets in my graph G. And the conjecture says that our principal families are the best that you can do even in this context. Now, you have to tell me that there must be some assumptions, because even in the ordinary Erdős-Koranda, which simply corresponds to the empty graph, everything is independent in the empty graph. We need assumptions, which is tempting to assume that K is at most the independence number of G divided by 2. Turns out that it does not suffice. We need slightly more. Mu of G is this characteristic. Formally, it is written here, but don't try to read it. It means that if I take any independent set of size smaller than mu of G, then I can always extend it to larger independent set. And now the statement is official, as I said. It's my last slide, not yet. So no, don't. So.
You're fine.
Yeah? Okay, so if I find an article, let's see.
Maybe I quickly pull up some more slides. Or?
No, I skip one topic. So let me finish this one and then we'll talk. All right. So again, when you see it for the first time, it's too good to be true, but the conjecture is over 20 years old. And so really lots of results, lots of partial cases have been confirmed. And so here is something which I find interesting, That's what much of the research was done. You have a bunch of disjoint copies of graphs, natural graphs, and it is solved by when those graphs are clicks. And in general, it is easier to study these things when you have an isolated vertex, because if you have an isolated vertex, then it's obvious it's the best center. Right, everything else is worse, you at least know what is the value. And this looks like a very interesting problem, so also open. We take a bunch of disjoints bipartite graphs and try to solve it in this case, but again, it is just an example. There are many more open problems surrounding this conjecture, both concrete and abstract. Questions? So, Mr. Chairman, what are we going to know? Are we going to just finish here, or I can briefly go through the topic that I skipped?
Probably, if it's 2 minutes, it's fine, but I suspect it's more than that.
No. I cannot do milliseconds, so
What?
I can do 2 milliseconds or 30 seconds, whatever you tell.
No, 2 minutes you can have, yeah.
Okay, good.
Even 3.
Okay, good. So let me then just very briefly tell you.
Sasha?
Yes.
Just a quick question about it. So if I think of a Boolean variable corresponding to every vertex, saying that whether it's in the independent or whether it's in the independent set or not, the principal family is kind of can be described by sort of a circuit of size 1, which is saying the ith vertex is 1.
A family is a higher order object. It's Boolean function. A family is a Boolean function. Alright, so now I have only 1 minute left. So that's another topic in Ramsey theory. There are a lot of research around so-called Ramsey numbers, because as I said, the Ramsey theorem can be formulated in the finite way. And Erdős and Heinel also long ago asked about their generalization. It probably does not make sense to try to read it in the remaining 30 seconds, but the idea is that in the Ramsey theory, they conjecture that there is a point somewhere which is t when something when the behavior of something changes from polynomial to exponential. So they proved it in one way, and we proved in another way, and also there is a couple of open problems here. Questions?
I have one.
Yes.
It's like more broadly, like not just your research, what do you think is like the biggest problem in combinatorics right now? Is it? I mean, I've heard it, this like Ramsey problem being cited as like the biggest problem.
This one?
Well, just like bounding Ramsey numbers.
Bounding Ramsey numbers is certainly. I am not sure.
What is, in your opinion, like the biggest question in combinatorics?
There are several problems in combinatorics that are major. There is a handful of them that I don't dare to rank. And one of them was actually solved recently, or almost solved, which is in additive combinatorics polynomial Feynman-Roger conjecture. So some of them are getting solved, well, at least in the finite case, some of them are getting solved. But I would not dare to reduce my personal list to less than 5 programs. At least 2 of them are here.
Okay, so let's thank Sasha. We already had some questions. Are there? It's open. Do we have additional questions? Okay, so great. Well, thanks, Sasha, again. And next week, if you did not have enough graphs this week, next week we're going to have graphs with algorithms on them. So Julie will be speaking and talk for you. Okay. Thanks.